Okay, let's unpack this. We are about to plunge into a deep dive where we connect the smallest unit of digital art, the single meticulous pixel, with the most complex systems of modern game engineering.
It's a study in purposeful constraint, really. We're moving beyond just, the simple nostalgia for classics like Super Mario World or Sonic the Hedgehog 2.
Yeah, we all love those.
We all love them, but we're asking what happens when that profound artistic discipline of pixel artistry meets the rigorous, scalable architecture of C# programming in an engine like Unity.
And that's a fantastic juxtaposition. We've been given sources that detail the core philosophy of visual precision. I mean, how to anti-alias by hand, the dynamics of hue shifting, fighting the dreaded banding.
All the classic stuff.
Right, and that's sitting right next to this comprehensive engineering log for a sophisticated 2D game project they call Mini Souls.
So our mission today is to synthesize these two worlds. We need to understand how the visual commitment to precision, where, every single pixel placement is a deliberate, intentional choice.
How does that translate into the practical reality of game development?
Exactly. I mean, you have to build code that's robust enough to manage physics, that can scale from one enemy to the whole battlefield and handle these really intricate boss behaviors.
That tension you mentioned, that's where the real learning happens. The art demands this meticulous, almost painful attention to detail.
Oh, isn't it?
While the engineering requires you to build systems that can abstract and scale that detail without losing any of the original aesthetic intent. This is, at the end of the day, the ultimate shortcut for you, the learner, to understand exactly how those beloved, enduring game worlds achieve their cohesion and their timeless feel.
So I think we have to start with a proper definition. This is where a lot of misunderstandings begin.
Right. What is pixel art?
Because not every image that's made of pixels is pixel art. I mean, you can zoom into a photograph and see pixels, but that's not what we want.
So what's the line? What separates it from just a low-resolution image or, say, a blurred digital painting?
It comes down to intent and control. The sources cite an expert, Alex H.W., who defines it as, the pixels must hold importance to the nature of the work.
They have to matter.
They have to matter. If the image can be created perfectly well without the artist ever zooming in to check or adjust a single pixel, it's probably not pixel art.
So it might be a rough sketch, something like Ookaki.
Right, but it lacks that necessary precision. The defining characteristic, then, is that the artist has to maintain complete control and precision over the composition, even at that microscopic level.
So every single pixel should be a purposeful decision.
Precisely. This is why just offsetting a single line of pixels by one space can drastically alter the perceived shape or even the mood of a sprite. It is an art form that is literally defined by its granularity.
And this whole emphasis on control leads us directly to the pixel artist's taboo against certain tools. The sources call them dirty tools.
Yeah, and that's a great term for them. Dirty tools are basically any function that automatically places pixels for you.
Like a blur or a smudge tool.
Exactly. Blur, smudge, smear, or any kind of automated gradient blending. The moment the computer starts making decisions for you about where to place intermediary colors or how to blend edges, you, the artist, have lost the explicit control that the medium requires.
That's a really helpful distinction, isn't it? It reframes the argument away from just, oh, you can't use that tool, and toward a real artistic principle.
It does, and it also explains the whole perennial discussion about color count.
Right, which can sometimes just sound like arbitrary nostalgia. Back in my day, we only had 16 colors.
It sounds like that, but it's not arbitrary at all. High color counts are flagged not because an artist can't use them, but because they often indicate that the artist has used those automatic tools.
Ah, I see. So those filters and blur effects, they generate dozens of unnecessary new colors to create those smooth transitions.
Yes, and suddenly you've got 200 colors in your palette, and the entire aesthetic cohesion is just lost. The visual language breaks down.
So the restriction isn't about saving bytes on an old cartridge anymore, it's about managing complexity. If you limit your palette, you're forced to make every single one of those few colors work as hard as possible to define shape and form.
Absolutely. Just think about the management overhead. Let's say you decide to adjust the lighting of your scene. If you have 4 colors on 4 simple ramps, that's fast, it's controllable.
You can tweak it in a few minutes.
But trying to adjust 200 distinct color values across a whole scene, it's nearly impossible to manage consistently. You're going to end up with a visually disorganized, chaotic final product.
Okay, so we've established that the single pixel is the smallest unit of construction. Yet the sources argue that the single pixel by itself is often near useless and meaningless.
Yeah, it often just reads as noise.
So if the single pixel is just noise, what's the signal? What's the thing we should be paying attention to?
The functional signal is the pixel cluster. This is really the fundamental unit of decision-making for a working pixel artist. We're talking about groups of contiguous pixels, all of the same color, that produce a solid color field.
So the artist's primary job then, it shifts from painting with individual pixels to almost sculpting with these larger clusters of color.
That's a great way to put it.
Yeah.
The artist concerns themselves with the shape that these clusters produce, and just as importantly, the negative space between them.
Can you give us an example?
Sure, think about the sprite of Little Samson from the NES game. His headband, his facial features, his hair. Each one of those elements is a powerful, distinct cluster.
And on the NES, you were so limited.
Extremely. You often had a maximum of 3 colors plus transparency for each sprite. That kind of extreme limitation forced developers to prioritize creating powerful, expressive shapes for these clusters. There was no room for ambiguity.
You're arguing the cluster is the true unit, but where's the line? I mean, does relying too heavily on large clusters risk making the final art look chunky or, less detailed, especially now that we're not limited by old hardware?
And that's the core trade-off. It's the essential artistic decision. If you use clusters that are too large, you risk losing subtle forms. And yeah, it can look crude.
But if you go the other way?
If you go the other way and focus too much on breaking everything down into individual pixels, you risk introducing that visual noise we talked about, where the eye just struggles to form solid shapes from all the tiny dots.
So the mastery is in the balance?
The mastery lies in finding the ideal size and shape for each cluster to convey the intended form with the maximum possible efficiency. It's about using the cluster to define the shape, and then using single pixels only for those ultra-fine details or for manual anti-aliasing, which I know we'll get to.
So the process starts big, not small. You start by blocking in a silhouette, segmenting it into these major color clusters, and only then do you start refining the shape.
Exactly. If the clusters aren't powerful and readable at the start, the final image is going to fail, no matter how much polish you apply later on.
Okay, so once we understand the cluster as our building block, we need a language to make those blocks cohesive.
And that means color theory. But it has to be tailored specifically for pixel art.
The sources strongly, and I mean strongly, advocate for shifting away from the standard computer RGB model.
Oh, absolutely.
They push for the HSL or HSB model. That's hue, saturation, and luminosity or brightness. Why is that framework so much more intuitive for a pixel artist?
It's because RGB red, green, blue is machine-centric. It just describes how light mixes on a screen. HSL, on the other hand, is human-centric. It's how we perceive color.
Can you break that down?
Sure. Hue is the identity of the color. Red, blue, green. Saturation is its purity or intensity.
Yeah.
And luminosity or brightness, that's the critical factor.
Yeah.
It's how light or dark the color is.
And when you're trying to create depth on a 2D plane, you're mostly just playing with light and shadow.
Exactly. You're primarily adjusting luminosity to define form. And HSL lets you make those adjustments without accidentally changing the color's core identity or its purity. It's a much more controlled way of working.
And within that model, the single most important principle seems to be contrast.
Absolutely. Pixels are just little blocks of color. The entire visual language relies on the difference between the adjacent blocks.
High contrast defines shapes.
Right. And low contrast colors blur together and make the form look flat. You get this muddy-looking sprite where the light source is totally undefined. It's a really common beginner mistake, keeping their light and dark values too close together. It just starves the art of any dimensionality.
To create that crucial spread in luminosity, artists use something called color ramps. These are groups of colors arranged by brightness. Now, most beginners, myself included, would probably start with a straight ramp.
Which is just changing the brightness value.
Yeah, just making the same color lighter or darker. But you mentioned a much more sophisticated technique, hue shifting. Can you explain how that fundamentally changes the artist's workflow?
A straight ramp, it looks digital, it looks flat, and honestly, it's often lifeless. Hue shifting is the practice of subtly bending the color's hue as you change its luminosity.
So you're not just changing one value, you're changing two.
That's right. As you move toward darker colors, the shadows, you bend the hue toward the cooler end of the spectrum, so blues, purples, cyans. As you move toward the lighter colors, the highlights, you bend the hue toward the warmer end yellows and oranges.
Which reflects real-world physics, doesn't it? You know, the blue ambient light from the sky fills in the shadows, and the yellow sunlight creates the highlights.
Precisely. That's why it works so well. This technique adds so much depth and subtle contrast without increasing your color count at all. It makes the shading feel organic and reflective of a real light source. It immediately improves the visual quality and gives this illusion of complexity using the exact same number of color steps. This is mastery of the medium.
And this mastery loops right back to what we said earlier about palette conservation and cohesion. We talked about how a smaller palette is easier to control, but how does it promote cohesion across an entire game world?
A cohesive palette acts as a visual glue. It's as simple as that. If every single asset, player, the enemies, the environment tiles, the UI, if they all draw from the same limited, carefully hue-shifted palette, everything looks like it belongs in the same order.
It creates a unified texture.
It does. If you have 200 colors, the chances of two unrelated colors accidentally entering the mix and causing visual dissonance, it just increases exponentially. A tight palette ensures visual continuity. It really cements the player's connection to that specific game world.
Okay, let's pivot from the theory of color to the application. Shading. The goal here is to convey three-dimensional form and depth on a 2D surface, which requires establishing a light source.
It does, and this is where we meet the most famous enemy in all of pixel art.
Pillow shading.
The great evil. Pillow shading is the definition of lazy shading, and it is a cardinal sin in this art form.
So what is it exactly? It's when you surround a central area with increasingly darker bands.
Yes, often in these concentric rings, completely, regardless of where the external light source is supposed to be coming from.
So instead of shading based on how a 3D sphere or cube would be lit, you're just following the flat 2D geometry of the shape that you drew.
Exactly. And it makes objects look soft and spongy and undefined, hence pillowy. The mistake is relying on the internal shape rather than simulating an external light striking a 3D form. You have to always conceptualize the object in 3 dimensions before you start placing your clusters to mimic the fall of light.
So if your ship is meant to be a cylinder, the light should fall along that curved surface.
Not just in circles around the center. It sounds obvious, but it's a trap almost everyone falls into at first.
And what about the color extremes? We're talking pure black and pure white. Why are they so often discouraged for general use?
Well, pure black, which is hex code, hashtag 000000, and pure white, hashtag FFFFFF, they're just often too harsh for most internal details. Real shadows, even in the deepest recesses, they reflect some ambient light.
So they have a subtle color.
Right, often that cool glow or purple we just talked about with hue shifting. Using pure black internally separates elements too harshly. It flattens the image. The advice is to reserve pure black strictly for high visibility game outlines, which is an aesthetic choice for clarity, or maybe for specific tiny details like pupils.
And pure white, same logic.
Same logic. Pure white is really only permissible for very specific justified uses. Specular highlights.
The glint on metal.
Exactly. The tiny points of intense reflection, like the glint on polished metal or wet surfaces or magical effects. Anything less than that should be an off-white that still contains a subtle hue, maybe leaning a bit yellow to reflect that warm light source.
Okay, so once we have the shading complete, we inevitably face jagged lines. And this leads us to the meticulous, painstaking process of manual anti-aliasing, or AA.
Manual AA is the hand-placed smoothing of jagged edges. Use buffer shades. These are intermediate colors placed specifically to ease the color transition from one cluster to another. It's a very slow process, but is absolutely necessary to retain that crispness while softening sharp geometry.
And the pitfalls here are incredibly subtle, but they can be fatal to the aesthetic. Let's start with over anti-aliasing.
Over AA is when you use too many buffer shades or you spread them out too far. The moment you use too many colors to soften an edge, the image loses its defining crispness.
It just looks blurry.
It looks blurry, which completely defeats the purpose of choosing pixel art over a higher resolution medium in the first place. Good AA should be basically invisible until you zoom way in.
And then there's a related problem called AA banding. This happens when the buffer shades themselves line up in a pattern that, ironically, reveals the underlying grid you're trying to hide.
Right. When those buffer pixels line up perfectly, they don't blend the edge. They actually highlight the grid structure. The line looks segmented and unnatural, almost like a staircase.
Now how do you fix that?
You have to manually break up those lines. go in, pixel by pixel, and adjust them until the pattern is disrupted and the eye perceives a smooth, continuous line. This is truly the sign of a veteran artist. They're not just drawing, they're actively fighting the grid itself.
And finally, a really dangerous technique called sellout or selective outlining.
Sellout is where the outer outline of a sprite is blended, not to another internal shade, but to a specific background color.
Okay, so when would that ever be a good idea?
Well, it's often used when the background is guaranteed to be a solid color, like a dark blue or black space scene. But, and this is a big but, if that sprite ever moves over a varied background, like a light green forest tile.
You get a horrible, ugly halo effect around the character.
Exactly. It's a technique that sacrifices portability for a quick fix on a static screen. It's generally a bad practice in modern game design, where assets need to be flexible.
The next technique we have is dithering. And this is fascinating because it was born out of hardware constraints, but it still serves a purpose today.
Historically, dithering was absolutely essential. If you had an old console with, say, a 16-color palette, and you needed to transition smoothly from a dark blue sky to a light blue ocean, you couldn't just create a gradient.
You didn't have the color.
You didn't have the colors. So you used dithering, interlacing the two available colors and patterns like a checkerboard, and you relied on the human eye to optically mix them into a new, perceived intermediate color.
So today, when we have 16 million colors available to us, why is dithering still used?
Well, it's no longer primarily for creating gradients. Now it's used much more selectively for texture.
To imply roughness, like sand or moss on a brick wall.
Exactly. Or to provide a final soft taper to an opaque edge.